circuit ground has got a lot of problems associated with it. Been working as an engineer for 40 years. Lots of times when something doesn't work right, it's the circuit ground connections. If you look at the schematic, you see all this variety of different symbols. We've got a pointer here somewhere. Killing myself. There we go. You know, you see that ground symbol is the most common, the oldest one. Sometimes you see a triangle, easier to draw. That's lots of times used for chassis ground. Then you'll see grounds with a little letter on them, an analog ground, digital ground, a power ground, and isolated ground. See that? Because systems will have a lot of grounds, and you got to say, well, what is a ground, you know? Well, the ground is a kind of a common point for a circuit. So within one circuit, all voltages will be referenced to that ground. In SPICE simulations or computer simulations, it's node 0 on the circuit. On an automobile electric system, it's a frame of the car. I don't know what they do with fiberglass cars. That must be interesting. But anyway, they do have a variety of symbols for it, and grounding has caused a lot of problems for me over my years. So I'm going to be kind of looking at some of the cases, like when your circuit ground joins the dark side, basically. Okay, and one of the first things I'm going to look at is a microstrip thing, just because I had a good example of that a while back with a commercial product that didn't work real well, and you know, ended up redesigning the ground system on a circuit board, and it considerably improved performance. Okay, so with a microstrip, there was just thing involved a lot of microstrip problems. You have a ground plane underneath which seats some metal. You have your microstrip, but this is a cross section where the strip line or microstrip is running away from us or towards us. That direction there is our cross section. You'll have electric field lines and magnetic field lines involved between those things. And microstrip, of course, not quite perfectly shielded because you have a solid dielectric here, you have air dielectric there. It makes a slight difference in propagation. So they aren't perfect, but this would be a quite happy microstrip. It'd work as well as they do there. I'm going to look at the microstrip that has a little problems, problems I've seen on circuit boards. You get a microstrip, there's your main strip line. And you got the fields. Well, some of those field lines are going to go into a trace next to it. You have a power trace right next to your microstrip. It's going to couple between them. As a matter of fact, you can even make a component called a directional coupler. So if you get noise traveling one direction on the power trace, it'll actually introduce a noise going the opposite direction down the microstrip because of the characteristics of the directional coupler. So that will be a less happy microstrip, so to speak, depending upon what the spacing is between this. If this is 3 or 4 times the width of the microstrip away, yeah, whatever you want on the power line, you'll probably not see any trouble. In some cases where stuff needs to be run close, they'll actually run another little strip in between, which will have a bunch of little via holes hooking the circuit board to ground there. Again, it's to keep signals where they belong. Okay, now this is a particularly interesting microstrip. I've actually seen that problem show up several times in the past, not just on this one product that was in trouble there. The microstrip, somebody needed to run a power trace there, and somehow or another the power trace ran for a couple inches right smack under the microstrip. So it's done a couple of things to the microstrip that's not good. First, the ground isn't a continuous piece all the way underneath it. Whenever you have a signal going out, you want a return path for it. People sometimes forget, well, the signal has to return. Current flows in complete loops, and well, wherever that return path is, it can make problems. So putting a power trace right in the middle of the return path, and we'll see it in a place where it actually wasn't a product that was even worse than it looks here. But this is definitely not a happy microstrip. This, you'll have signals coupling back and forth everywhere where you don't want it. Now, this was another microstrip thing I ran into. It's quite interesting. This is looking from the top, and the gray is the grounded area. And somebody needed to get some traces across there, so they run right under the microstrip. Well, this is a serious violation that the signal is going along this path, whereas the ground is having to go out there and back there, so the ground currents aren't flowing the same path. And that can actually make a little circuit or structure called the slot antenna. You can take a sheet of metal, very large sheet of metal, and put a slot in it of the right size, and hook a coax across the slot, put it on the side of an airplane, and you have an antenna that sits flat but yet radiates very well. So this is an accidental slot antenna to some degree here, and I'd actually seen problems where I'd doing FCC 15 testing on a product I've been involved with and not watching the draftsman very careful, not giving the draftsman enough baseball cards, another story. But anyway, we had a trace that was running a high-speed clock, and there was a little slot in the ground plane, and 10 megahertz clock, and 10 megahertz was everywhere when we started running it. Fortunately, it was found before it actually went to the test lab, but it was fixed. But that type of thing is a common problem because circuit board designers aren't circuit designers, and you got to learn to work with those folks because they can do wonderful work if you work with them. They're smart people. You just got to give them the right info. Okay, and this is the actual circuit board where I showed up with a bunch of difficulty. And this lower picture here is a picture of the bottom side of the same circuit board that has been mirror imaged in one of the photo programs there so that you can see it. So you can see what lines up with what. And then I drew these black boxes. I probably should have used a purple or orange or something for the boxes to make them a little clearer. But anyway, that box and that box are the same thing. So you can see there's my microstrip running signal from a receiver circuit, up to a mixer area on a receiver. So receiver has got this part of the microstrip right here. It's got a power trace running right under it. You can see here where I was trying my first attempts to do an improved repair on it, where I cut the power free of the trace in every place where it was underneath there and ran little ground straps across here. And that improved things, but not as good as I wanted. By the way, the particular receiver started out at 2.5 dB noise figure, and after just fixing a lot of grounding related problems, it went down to 0.8 dB. So that's a substantial improvement in noise figure, just making sure the ground signals go where they're supposed to. This one gets a little worse yet, because that same power trace goes over here, that goes up to a filter, down to the filter, to the receiver mixer. Well, these are your LO and the IF ports, and you might notice that same trace is running right underneath the part of the traces for the LO and the IF ports. So many circuits, when they built that mixer, put a lot of effort into getting it very carefully balanced inside by their manufacturing and design process so that signals wouldn't get from one port to the other of the mixer. Well, here I've got this trace running along here that's coupling things from the LO and the IF ports right to the RF port of the mixer. I mean, so all that carefully built isolation was destroyed by a poor printed circuit layout. So something like a mini circuit's part or something doesn't work right, check your own layout first. It could be your ailment. This is another interesting thing that caused some ground problems. This connector was used at 432 megahertz, and it was mounted to the PC board with these two things here, and here's your ground and here's your center conductor for the BNC connector. And it's kind of interesting, they didn't get these two things, which could have been another source of ground. They weren't grounded to the shell of the BNC. They're just strictly mounting things to the PC board. So all of your ground at 400 megahertz is going back through this one little thing here, and this is up above the circuit board, so if you get any currents on the coax cable that's plugged in there on the outside, it comes in, the currents, ground currents don't go to the case, they go inside the box and the ground here, so you have effectively a coupling loop to make any signals that are picked up by the ground on the coax to actually couple them into the inside of the box. Not a good idea. By the way, one of the interesting things that I had on this particular box is that you could tighten or loosen screws on the cover of the box or wave your hand around and change signal levels, which was not a good sign. So the BNC connector had to go from 400 megahertz. It was used for a 28 megahertz point on the unit. And that's what I finally did with the BNC. I took an SMA connector, which is a better RF connector anyway, and mounted it on a little aluminum bracket that was tied right down to the ground plane. And I actually put a little piece of copper foil there to make the connection and leave it closer to a 50 ohm thing, even though it's a short run. they had an end connector on there that had you know, similar problems, and went through a lot of effort getting it grounded. And this is another thing that needs to be done with you know, microstrips. You got this grounded copper running right next to a microstrip trace, and this copper should be grounded at a lot of points along here. And I've heard of an example from Charles about I think it was a 10 gigahertz RF switch or something, that 4 of them on a board, 2 of them worked and the other 2 didn't. They appear to be identical layouts. And the whole problem was these little via holes which connect ground from the top to the bottom weren't there. And that'll turn an area like this into something that actually has signal currents flowing along at 400 megahertz. Again, at 20 megahertz, 30 megahertz, that type of thing would be perfectly acceptable construction. But we're talking 400 megahertz, 1420 megahertz, and maybe higher in a lot of the radio astronomy stuff. And a little violation like that could leave yeah, impedance bumps in the cable and radiation sensitivity. You could run the things where you put a finger on the circuit board here and the circuit quits working or becomes erratic. This is another one that I ran into. It was a bias tee. This one was actually used in a ham application at 432 megahertz, but it's exactly the same problem as 408, but transmitter signal went through it. You had a small capacitor between 2 connectors in a box, and then a choke to feed a DC voltage. So this would feed DC up to an antenna mounted preamp, and this would go to the you know, transceiver, receiver, whatever unit it's hooked to. But this was just put in a box, and the path between the grounds on these was somewhat longer than the path going across here. And yeah, the thing was quite an impedance bump. It was a real speed bump. You know how it is running over those in a parking lot. So the signal has a speed bump there. And on that one, you know, I had the thing in hand. I took removed that connector and just put a piece of copper shielding tape over the hole there to cover it up. Drilled another hole, mounted the connector right next to it. Capacitor down close there. So first capacitor, because it's close, it makes it closer to 50 ohms impedance over this little piece of effective transmission line here. And the ground path's exactly the same length. And all of a sudden now I've got something where it very easily goes through there. There was hardly any disturbance at all. It was just removing a connector. Yeah, keeping the ground underneath of his signal path is a very important issue. Now this was another one that was particularly interesting. It had a surplus signal generator from AIL Instruments or something. But anyway, it had intermittent performance. You could tap on the top of the case and it quit. Well, this coax cable that was here, this is a new one. But the old one that was there, it had a little plastic thing that was holding the shield in place, a pressure connection. And the plastic had cracked, and I couldn't get a replacement part for that. It was 30 years old. So I just soldered a new coax cable in here and said, that ought to have it fixed up. Made the new one a little bit longer so there was enough room to put it in the box. And it turned up that caused an odd thing. And of course the signal generator output had to go erratic at exactly 408 megahertz because that's the frequency I test things at. There's something about Murphy's laws, if I would have been trying to work on something at 350 megahertz, I probably wouldn't have even noticed it. But at 408, you move the frequency just slightly, and the output of the generator changes considerably. And I thought, well, what is going on here? And I don't know. The original one, this same coax cable was an intermittent connection where it went into the board there. So I didn't have a reference of what it was before. But anyway, took a look at that. It's actually a resonance. The way the circuit board is mounted, you can get a resonant cavity underneath here. And there was a resonance at 400 megahertz here. You could go with that thing and you place your finger on the ground plane. And by the way, where things don't involve high voltage or high powers, a finger test is very handy. If you touch a ground near something and all of a sudden it changes, there's currents in the ground. And this, you could touch the spacers here and things would go crazy. And so, it was a resonance here. I say, well, how do I break up that resonance? Because it also involved this cable. And the cure that made the problem go totally away was a chunk of ferrite. I unsoldered the cable there, shoved this chunk of ferrite over the cable, and put everything back together. And you could tune the generator from 400 to 500 megahertz, and the output didn't change at all. So it was all the resonance combined with this cable managing to couple into that resonant cavity formed underneath there. So, you can see some odd stuff when it comes to ground. So lots of times putting a ferrite on the outside of a coax is a good thing. And that's not something that's just, unique to me or us or other things. I've got an example piece of hardware right here. This I stole the connector off. I bought it at a Hamfest because I wanted the connector. So I've used a connector off this. But this was a piece of coax cable with a string of ferrites put along the outside of it, little rubber spacers between it. And that was to reduce currents flowing on the outside of the cable. And this, I think it came out of a piece of military hardware, more than likely. But anyway, pass this around so people can take a look at it. You can pull this one piece of rubber off and you take a look at what one of the ferrites looks like. It's got a whole string on them. And each ferrite increases the impedance of any thing flowing on the outside of the cable. So by the time you blend through this whole string of ferrites, you got pretty good rejection. And the rubber pieces in between, or so it could be a flexible cable to go between two pieces of equipment. So I'll go ahead and start that on this thing there. Nobody used that as a weapon. One of the things I noticed, it was heavy enough that Crowley, don't take that thing. He beat somebody up with that.
So that, the surface currents were causing the problem here too, apparently, right?
Okay, superset. I'm going to talk about that in just a little bit here. So that shows that whenever something strange seems to be happening, if you touch the outside of a cable or some areas near it, something strange happens. Try it, because you can get those ferrites on a clip-on thing, and they're not too expensive now, and you can clip it on. If problems suddenly go away, just leave the ferrite there. The ferrites are also useful, by the way, on things like the keyboard cable on your computer and stuff like that. Sometimes you'll see your, especially 408 megahertz receiver is receiving trash from somewhere, and you turn the computer off and it goes away. Well, it says put ferrites on every cable coming out of the computer. It's a common mode choke, and a lot of times it breaks up stuff. And sometimes one ferrite in the right place will cause a noise to drop by 20 dB. Talk about another one that was interesting. This is a contract job that I got that really paid quite well. Somebody built a industrial computer terminal for a special application, and it failed FCC 15 when they sent it to the test lab. The younger engineer, it's a very good digital guy, very good software guy, and really hadn't worked with RF. And he called me in there and called me, somebody I'd never heard of before calls me and says, can you be in here tomorrow morning? And I thought, oh, okay, you get good enough pay. So anyway, upon investigating it, the whole network cable had turned into an antenna because there was a missing ground. There's this little box, which I'm guessing what's in it, but that coupled between the network chip and the network connector that plugged in there, and there wasn't a ground right here. And the EMI dropped down on with a near field fold and a probe and a spectrum analyzer. It dropped by about 20 dB. And when somebody's failing by like 8 or 10 dB and putting a shield in one place brings you down 20, it says, okay, you got something that ought to pass. And when it was run to the test lab, it did pass. Other problem this particular box had was backlighting for a display with the fluorescent tubes are driven by RF. And the cabling for those got mixed with the power in cable, so we had a cable layout thing for the same box. But it was interesting. That was the greatest part of the problem, and a little spring clip that was fabricated to ground that case. Problem solved. It passed at the test lab with good margin next time. Talk about instrumentation amp. Lots of times we're running low frequencies, or as we'll see later, even higher frequency signals around. A normal op amp has 2 inputs and an output. Well, this one is really has 3 inputs, a reference and a plus and a minus, and feedback is internal. So unlike an op amp, you don't have any feedback resistors involved with the input. So no current flows in either input, and the output of an instrumentation amplifier is you take the difference between these 2 wires, multiply it by gain determined by this resistor, add it to this reference, and that's what's on the output. So if you have any problems with the ground, well, if you have a noisy ground here, you have a couple volts of signal right here, and a sensor of some kind here, it will never show up on the output from this noise source. you get a noise source in here. Well, if the ADC output or the ADC input return is hooked to this reference, then the output is trying to reference itself to the A to D converter's ground, and it washes it out. So I've seen a few cases where that's fixed things up using better amplifier schemes to fix stuff. And here, looking a little bit at the SuperSID type of thing and some things that can go on with that sketched out. This is one version. There are several versions of the preamps floating around. I'm not sure what's current now, but they have the thing with USB supplying power for it because they had a problem with the worldwide power supplies. That, there was a variety of voltages, and finding the right wall wart thing to ship along with your SID unit was apparently a problem. So it picked up power off the USB. Well, if you look at the situation with the USB in a computer does not do the best job of grounding things from an analog point of view. So you have your soundboard, which has an A to D converter here, and it gets a ground where on that board where it's grounded to the digital ground for the computer. You got the USB has its ground at a different point, and you got signals all over the place on a computer motherboard of many millivolts, which don't bother the computer. However, for something like this where you have a sensitive instrument, it's not a good idea. So you turn up with a couple ground loops. First, the power cord to the computer hooks to the earth ground, and if you look at earth ground at any two places, you find that it's got quite a bit of difference. Even two outlets in a house that are near each other but on a different circuit, you can look with a scope between the earth ground on one and the earth ground on the other, and you see there's a lot of trash floating around there. So you get your cable running out here where this cable might be a substantial length from a computer that's inside and a SID preamp outside at the antenna. And you definitely have a potential for, you got a ground loop here where you've got a voltage here from the garbage inside the computer, and it's trying to go to this ground, and this ground is hooked to this ground inside the board, goes back here. So it goes around, and you turn up with some of your switching power supply noise from the computer showing up there. In the case of the antenna circuit, you turn up with, if there's any leakage to earth ground at the antenna at all, you could get small currents, and this over a substantial difference in like a ground rod or grounded point out here, which isn't tied with copper back to there. You can see some pretty substantial voltages there, enough to really interfere with stuff. And I think I'd heard one report of a little wet weather, and you started getting some 60 hertz hum in there. And my bet is that there was some leakage path from moisture to these terminals to ground, and this ground is at a different voltage than this ground, and in comes the garbage there. One of the things that's a possibility, and need to look at it some more, maybe work with Tom on it, that if you want to use USB power, you could put a common mode filter in here, rather than a ferrite choke on the outside of the cable. You actually want to break the USB cable because it's only used for power, and put a common mode choke here. That has a good potential for breaking that loop there. So you get rid of one of the places where ground noise get in there. An instrumentation amplifier would be good to use here, except that instrumentation amps are quite a bit more expensive than a vanilla op amp. So because the SID is quite cost sensitive, that may not be a practical solution.
There's another architecture called a current amplifier, I believe. That might work too.
Current mode feedback, I don't think would solve that one. You still tend to show up with the same ground loops. Current mode feedback is a good way to extend bandwidth for a given silicon technology.
Yeah, okay.
That's its main claim to fame. And another one I'm looking at, line chip is an example of differential signaling, and their schematic. This was actually of the Blade RF board because I had the schematic handy at the time, and I didn't have the Razer schematic handy at the time, so I grabbed that and cut a little piece out and put it here. But you've got some kind of balun here to convert it to from your single-ended input to differential, and then it's differential going into the line chip because it's inherently differential. You look at the data sheet on the line chip, every signal inside there is running differential, and that's how they got by running all the analog and digital signals inside the chip without having ground loop problems and stuff inside the chip, which is a common problem. I've seen that in the past on a custom chip I was involved with that how easy it is to get ground. Well, yeah, you can't get a 0.1 ohm or 0.01 ohm ground resistance on a chip. It's many ohms in the traces on a chip. So their answer to that was to go differential signaling everywhere. And that was the answer that made that workable. Now, if you look in the Raspberry board, they used, instead of a Balun transformer type of thing here, they used dual pi networks, one low pass and one high pass. And I say that as a mixed blessing. It's got less loss than the ferrite transformer. And, but it also could mess up your balance a little bit when you get away from the center frequency where the pi networks were designed. So, well, that's a Raspberry problem when those guys are investigating that sort of thing very well. And then another thing I want to talk about is RS-422 or 485. That I've seen those a lot in the industrial world for serial communications. You know, normally your computer has an RS-232 port on it. You bring the RS-232 out to RS-232 peripheral. But if you're running your wires any significant distance, RS-485 is a differential signaling rather than a signal to ground kind of thing. So it has a potential for breaking up ground loops, and it'll allow up to 7 volts difference between the grounds of the two devices and still have the thing, signaling perfectly. There's different speed ranges available there because you have to terminate the network if you're running at very high speed. So if you're running under 100 kilobits, you don't get 100 megabits driver and receiver. You get the low speed one, so you don't have to worry about the slew rates, the noise, and everything else. So that does have to match. A lower speed part, no terminating resistor. Linear technology makes a series of parts. This is an example one where the two grounds can be up to 25 volts apart and the part still keeps signaling perfectly. So it's acting just like an RS-232 link, except that the grounds can be 25 volts apart and it still works perfectly. And it's up to 60 volts without damaging anything, and a couple of transit diodes in the right place can assure that you don't get that. So quite an effective way to do that. Oops, I hit 2 of them. Okay, and difference between 422, RS-422 you would run, it's a run like an RS-232. It's a full duplex thing, a separate pair of wires running each direction. True RS-485, it runs full duplex over cable, so you have to have transmit receive arbitration built into the software on both sides. I've actually seen 485 used a whole lot industrial. Down the middle of this, you got terminating resistor at each end, but this cable in the middle, it can be broken in 6 or 8 different places and put another RS-485 device there. And as long as only one device talks at a time, all is happiness with it. So it works well with the party line. They're useful. By the way, I've also used RS-422, 485 drivers just for driving things like phase switch signals for a phase switch interferometer, control signals. Even though they're intended for serial communications, just a 1-bit control signal could very easily go through one of those driver receiver pairs. And again, it breaks ground loops.
Bruce, have you done anything with the USB to the RS-232 connector adapter, since laptops don't have RS-232 ports as much?
Okay, I've played a little bit with some of those RS-232 converters, and they've worked okay, but I've only used them over small distances. If I have to run something a long distance, I would convert 232 to 422, so I got differential signals, and they go through the 100 feet of wire out to my antenna where I have to control something. I would not run an RS-232 more than about 10 feet personally. I mean, it's great for hooking a local device to the computer, except, well, computers don't have an RS-232 port. You have to put a dongle device on there. Other things to watch out for, the broken coax. When I first put my radio telescope receiver together many years ago, I had a lot of erratic performance. I could never figure out what was going on. I mean, sometimes worked just perfectly happy, and then would all of a sudden quit. And well, the modules that were hooked together are all hooked to the same chassis, so they had a ground path. And I had Hamfest coax cable there that ran between two modules, and it was a really pretty cable. I mean, you know, an SMA connector on one end and a BNC on the other, and it looked very well built. Well, it turns up that if you, after I finally bumped the cable at the wrong time, I realized the shield was actually broken. That cable had been flexed so many times, the shield was broken. And sometimes it would make connection and sometimes not. When it lost connection, the receiver wouldn't quit working because it had the ground path through other stuff, but it was definitely a very bad ground path and it would go erratic. And if it quit altogether, I might have found it quicker. You know, and you know, a broken shield like that is almost always intermittent. You know, you breathe on it wrong, the phase of the moon changes, you know, the cat walks by outside, whatever, you know, the cable, you know, makes and breaks connection. So it could be a real aggravation there. And that is it for the odd ground things I wanted to toss out here. There's a, you know, a couple cases brought up in the paper and the proceedings that are, you know, slightly different from this. Read them. Anyway, questions? Yes?
I got two comments. One on your microstrips. I found out the differential between two-layer board and four is only about 10% now. So if you go to a four-layer board, that gives you solid ground underneath all this stuff.
That is a good point with it. Yeah, once you get that solid, although the one where I got bit with the accidental slot antenna was a four-layer board.
Yeah.
I wasn't watching over the draftsman. I later learned that the draftsman, you give him really specific instructions and he gets grumpy, but the guy loved baseball cards. So when I give him a messy assignment, I'd give him a pack of baseball cards, which cost me $1 at the 7-Eleven store. And he was all of a sudden real agreeable working for me. And then when the whole thing was done and I was satisfied, I wouldn't give him another. So for a little over $2, my PC layouts were almost perfect. Other people said I was bribing him. I said I was incentivizing him. You know, matter of perspective. But yeah, amazing the things that make people work well. Any other? Yes?
It says software-defined radio, like these little dongles. Is it preferred to separate the USB ground? I know some people will pull the shell off the USB connector.
Yeah, that's a really iffy thing because you have the good possibility of generating radiation at some frequencies. I mean, USB was designed to have that ground there, and you're kind of violating the USB rules. I think I'd be more inclined on the antenna cable to put a whole bunch of, chokes there. And by the way, I did have one other thing in my short notes. I put it in here. Yes, I put it in here. You mentioned the USB dongles, and place where I was working just before I retired, we had something where we put a bunch of cell phone radios in a instrumentation package, and a cable got made wrong. And when they, so all of a sudden you have all these cables. The connector on the other end was pretty expensive, so they cut it off. So I have all these cables right here, which one end of them has an MCX connector, which is the same as used on those little USB dongle units. The other end is just a plain piece of coax. It's put your own connector on it. I don't know how many of them are here. Nobody take a handful of them, but if anybody wants to take one or two of them while they last, they're here. Anybody got an immediate need for one? A couple people. Okay, so I kept a couple of these for myself. I said I don't need this pile of these, and hopefully somebody can use them. Like I said, it plugs right into the dongle, and I've got one cable that I've played with a little bit, works fine. Yeah, I think that's.
Say something about clip-on ferrites. They're not all created equal.
One of the things with the clip-on ferrites, because normally if you put a ferrite sleeve on a cable, if you get a solid sleeve and put it on there when the cable is made, you turn up with a nice complete ferrite. Clip-ons, the problem's not the ferrite itself, but some of them have a plastic clip that doesn't put enough pressure on it. So the two halves of the ferrite, these two shells go together, and there's a little gap there where it didn't push together perfectly because the clip is kind of crappy design. And so if you get a cheap one, you're likely to find they don't get it, or sometimes you can wiggle them a little bit and seat them afterwards and they'll work better. But I have seen that before where a ferrite doesn't work quite right. It doesn't break up common mode currents, which is usually what you want it for. And all of a sudden it works great. You get a new clip on the same piece of ferrite. They do need to be held so that the both sides of that, those polished surfaces are pushed together rather firmly.
What I was talking about is they don't work over massive frequencies.
Oh, well, yeah, all ferrites, by the way, they have a frequency range. Look it up in the catalog. You know, for a particular ferrite, you see ferrites that work good at low frequencies, and at 50 megahertz, they just lose the ability to choke off signals. They're hardly there. You'll see another grade of ferrite that it begins to work a little bit at 30 megahertz coming up, and it'll work to about 300 maybe. And then there's another grade of ferrite that begins to work about 200 megahertz and gets real good at 300, and then goes on up in there. And there are cases where I've put 2 ferrites or even 3 ferrites next to each other that are 2 or 3 different flavors of it to make a wide band choke thing. So yeah, I appreciate you bringing that up, because yeah, I have been burned by that sort of thing and have had to do it before and just didn't make the paper. Any other questions, comments? No tomatoes to throw at me? Thank you.